Okay, let me distract you by talking about some probability problems and Chebyshev's inequality and such. Let's go back to those problems like, there was number 26 in section 12.6 about the size of a study. Okay, in that particular problem, we plan to survey, okay, but that's in the future tense. We're going to survey some number of people for seasonal affected disorder. So we're looking at binary random variables. X of I will be 1 if the ith person in the survey has seasonal affected disorder. So it's 1 with some unknown probability p, which we're trying to determine. Or it's 0. And then we look at how many people we get who reply yes. So if we add up these zeros and ones, that will give us the number of people with seasonal affected disorder. If we divide that by the sample size n, this gives us the fraction of people who replied yes. And we hope that x bar is close to p. And there's some basis for that hope. We know that the expected value is p. And we know the variance. The variance for an individual x of I is p times 1 minus p. And the variance for the average, and the standard deviation for the average is the square root of this. But then we've always been focused on a certain equation. We want the error to be small. That is, we want x bar minus p in magnitude to be as small as we can. And typically, we're given some maximum allowed error. Some value for epsilon close to 0. We'd like the error of our estimate to be small. Well, we can't be sure, but we want some high probability. So we're given some minimum degree of confidence, call it. That is the number c. So epsilon is probably close to 0. C is probably going to be close to 1. We want to be pretty sure that the error is small. And we want to find the sample size. We want to know what sample will we have to go out and get to be pretty confident that the error is small. Well, so you did this problem. By applying the central limit theorem. It's the pill problem. To use the shortcut, we have the equation z is 2 epsilon times the square root of n. Comes from using the worst case estimate for the standard deviation, where z depends on what c is. C tells us what z value we'll need. And this is an equation we can solve for n. Square root of n is z over 2 epsilon, so then we need to square that. Well, let's put in some numbers. Suppose we're given maximum allowed error is 0.05, and we want C to be 99%. We want to be 99% sure that the error is this small. Then we can find the sample size. Our z value for 99% has to be well, we look for a number phi of which well, it's got to be 99% plus one of the tails, 0.995. So that gives us our z value. And well, one more line on this board. So n is 2.58 divided by twice 0.05. This thing squared, 25.8 squared. That is, a study of size 666 would be enough for us to say here with 99% confidence that the error is going to be bounded by 0.05. There's another way to look at this. What if we apply Chebyshev's inequality? So we want this equation to hold. So looking at the complement, we want the probability that the error is big. Okay. More than epsilon. We want that to be 1 minus c. Now, the reason I'm looking at the complement is to make it look more like Chebyshev's inequality, which has a greater than or equal to sign here. And so let's look at this. And see what we can say about the probability that the error is large. Well, first of all, a very small thing. Chebyshev's inequality actually has greater than or equal to. So let's write it that way. If anything, that makes the event a tiny bit bigger, so the probability at least won't go down. And Chebyshev's inequality says that's bounded by the variance of x bar. Well, the variance is p times 1 minus p over n, but we don't know p. But as in the central limit theorem method, we can take a worst case estimate for p. So p is at worst a half. 1 minus p is a half. Product is a quarter. And then we divide that by n. This over epsilon squared. Well, so it's a compound fraction. Clean it up. So Chebyshev's inequality says, probability the error is large, is bounded by this. And so we would, it's enough to make that to be 1 minus c. Okay, so we have that guarantees that well, not that this probability is exactly equal to 1 minus c, but it'll be that or less. Probability that the error is large is going to be some, we've got an upper bound on it of 1 minus c. And so we can solve this for n. Okay, so let's do that. So we take reciprocal on both sides. So the 1 minus c is now on the bottom. And then we have that 4 epsilon squared. Well, let me move the boards around. So to go back let's try plugging these same numbers in. We're given that c is to be 99%. Epsilon is 0.05. And what study size do we need? Well, let's plug it in. 1 minus c is 0.01. So what's 4 epsilon squared? 4. 5. Multiply this out, we get another 0.01. One over 100 here, or 100 there. We need n to be 10,000. Different answer, right? Well, they're both correct. That is, taking n to be 10,000 would be enough to be 99% confident that the error is this small. But a study of size 1/15th of that, only 666. I mean, beastly as that is, it would be enough. And if you're asking NIH for a grant to do this study, they would much rather fund a study of size 666. The central limit theorem is a much sharper tool and gives a sharper bound for how many people you have to survey than Chebyshev's inequality gives. Well, let me do another problem in which there are two different things I want to say about it. And this is a problem you've seen before recently. Problem number 6 on our practice second midterm. It's the pill problem again. Same situation. But we're given n. We plan to survey 100 people. And we're given C. It's 95%. And we want to find for what error, epsilon, can we be sure probability of x bar minus the unknown true probability p, and that for what margin of error can we be 95% confident that we'll get an estimate within that allowed error? Well, so you did this problem. It's the pill problem again. X bar, by the way, in this problem was called E hat for the estimate. And to do the shortcut, we can apply that same equation, and only now we're given n, it's 100. And we need the z value for 95%, which is 1.96. Because 1.96 gives us that 95% plus the left tail. Well, so you found epsilon was 1.96 divided by twice the square root of 100. Yeah, a tiny bit less than 1/10. Well, okay, so you did this, but let me rephrase that in terms of intervals. That we're 95% confident that P is in a certain interval, E hat minus epsilon, E hat plus epsilon. And that's sort of just rephrasing what we've said. We're going to get some estimate for the disease prevalence, and we'll be 95% sure that P is in this interval. the length of this interval is just 2 epsilon. We don't know the center yet because we haven't done the study. But it's okay, 2 epsilon is a bit less than 0.2. Well, it's 0.196. Now then, on to chapter 2 of the story. Suppose we go out and do this study. Problem 6 just was talking about some future thing. So here's the sequel to number 6. We take our random sample of 100 people, and we find that 10 of them have the disease. Now what? Well, more specifically, what's a 95% confidence interval for the prevalence of the disease? And then we can compare it with our 95% interval that we had before we did this study. The difference is that now we have some additional piece of information. So we found that 10 people had the disease. So the fraction of the survey group with the disease was 1/10. Which we hope is close to the unknown prevalence rate p, but we want to say that quantitatively. We want a confidence interval. So so to work out the standard error, okay, this is the binary case, right? Binary random variables. So we have that formula for the standard error, e hat 1 minus e hat n minus 1, the square root of that. Okay, so 0.1, 0.9. Well, since without a calculator, let's change 99 to 100, and it'll be close, and we can take the square root. Square root of 0.09 is 0.3, right? Try it. Square this, and you'll get 0.09. Square root of 100 is 10. Standard error is 0.03, and so we know what the confidence interval is going to be. We have the same z value, of course, because it's still 95%. So we want to go take the interval from e hat minus z standard errors, e hat plus z standard errors. And that interval is, well, I did the arithmetic ahead of time. goes from 0.04 and a little bit up to 0.1588. Yeah, with only 100, we're not getting a real short interval, but we're getting a shorter interval than we had before. If we subtract these two numbers, yeah, this interval is only 0.1176 long. It's shorter than the interval we had there. In fact, it's 60% of the length we had before. And the reason we are able to narrow down on p more precisely, that is with a shorter confidence interval, is the additional information. Here, we're not using the worst case estimate for the standard deviation that we had to use over here. Instead of using a half right there, we use something that was only 60% as big. And we get, with 95% confidence, a slightly shorter interval. But that's after we do the study and we have some idea of what the sample mean is. Well, let's do one more confidence interval problem where the random variables are not binary. We're not going out and surveying people yes or no. We're going out and surveying and saying some other question. And we can make a confidence interval if we know what the data is. Well, we take a random sample of size 100 again. So our value for n is 100. And we try to get some random sample so we have independence, so forth. So we get these 100 measurements, x1, x2, x100, and suppose they add up to 820. Well, so we know the sample mean, it's 8.2, but that's not going to be enough information to calculate, say, the sample standard deviation. But suppose we also know what the sum of the squares of the measurements are. That it's 7,700. Okay, so we don't yet have the raw data. We're not told what these 100 numbers are. But let's see if this is enough information to figure out, say, a 95% confidence interval. For the mean value of whatever it is we're measuring. Well, sample mean is obviously 8.2, so they're certainly not binary measurements, because I mean, the average measurement was more than 8. The sample variance. Well, one of the equations for the sample variance, one of our two equations for the sample variance, use the sum of squares. So let's try that. It's the sum of squares, okay, divided by n minus 1. And then we subtract the square or the sample mean, but with this fudge factor. Yeah, so we have enough information to determine the sample variance. And I've already done the arithmetic. This is 9.859. So the sample standard deviation asks the square root of this. Well, the square root of that turns out to be 3.14. Standard error, we divide that by the square root of 100, 0.314. We want a 95% confidence interval, so we know what our z-value is. We need a number z, phi of which would be 0.975. So our confidence interval and x bar minus z standard errors up to x bar plus z standard errors. Okay, and we have enough to fill this in. Goes up to 8.2 plus our z value. Okay, which gives the interval 7.58 up to 8.82. An interval centered at our sample mean, 8.2, and we're 95% sure that the mean measurement is in this interval. The point of the problem is that we don't actually need all the raw data. We don't need all 100 measurements. Knowing the sum of the measurements and the sum of the squares is going to be enough here. Here's a different sort of problem. Going backwards in time, which we'll do today and also on Friday. Suppose we have some random variable. And we want to determine its expected value. And what we're given is the following equation for the cumulative distribution function. Okay, which our favorite letter is capital F for the cumulative distribution function. And it's this. It's 2 over pi times the arctangent of x. Well, that's what it is when x is positive. It's 0 for when x is negative. And we want to find the expected value. Well, sounds okay. We know how to get the density function, right? And so we know what to integrate. Let's first of all, let me argue that this is a bona fide possibility for a cumulative distribution function. That is, it's a non-decreasing function that goes from 0 to 1. The graph of the arctangent function looks like this. And you take one branch of the graph of the tangent function and turn it sideways. It goes from minus pi over 2 up to pi over 2, which is why the problem has thrown in a 2 over pi, so that this function will approach 1 as x increases. And we've also thrown away the left half of this and made the function 0 for negative x's. So to find the expected value, first we'd like the density function. And we know that's going to be the derivative of capital F. Okay, so we take the derivative. Uh, 2 over pi times the derivative of the arctangent function. Well, let's assume everyone remembers that the derivative of the arctangent function is 1 over 1 plus x squared. That was rather surprising back in 3A or whatever it was, that the derivative of the inverse trig functions did not involve trig functions. It's just this rational function. Okay, so now that we have the density, we need to integrate it. The expected value, integral from minus infinity to infinity, of x times the density. Okay. We know how to find the expected value. We take all the things the random variable could be and weight it with the appropriate probability, f of x dx, and add them up. Well, of course, the density is 0. I should have written the density is 0 for negative x. So in this integral, nothing happens until we get up to 0. Yeah. So but what I should have said is that the density is given by this for positive values of x, but it's 0. Differentiating the constant 0 is easier. So we look at this integral. And see if it's something that we can figure out how to integrate. it cries out for a substitution. In fact, to make things a little easier, let me move the 2 inside. If we substitute for 1 plus x squared, it's going to make this a whole lot easier. Because then the denominator is just 1 plus x squared. du is 2x dx, which we have sitting here. So we do this substitution. And we just have 1 over u, du. Okay, so let me write that down. So that wasn't so bad. When x is 0, u is 1. So we're starting at 1. And then u goes off to infinity. An antiderivative for 1 over u is just log u. Well, log absolute value of u, but it's positive here. And for the lower bound of integration, when we plug in 1, well, log of 1 is 0. That's the easy part. But what about the upper bound of integration? If we plug in infinity, that is, if we take the limit of log u as u goes to infinity, this does not converge. It's going off to infinity. The point. We've been talking about expected value of random variables. We've never actually promised that they exist. Here's an example where, well, we're not sure that this cumulative distribution function could ever come up in an application, but we could at least invent this function where the random variable x doesn't have an expected value. That is, its expected value is larger than any number you might think of. And we've kept it a secret until now that that could possibly happen. I don't want to demoralize people who are looking for expected values. See, time to do this problem. Okay, I think we better stop here for today.